In this example, we're given three vectors, v sub 1, v sub 2, and v sub 3. We want to determine if they are linearly independent or linearly dependent. If they are dependent, we want to find a dependence relation between the vectors to express vector v sub 3 as a linear combination of v sub 1 and v sub 2. Looking at the notes below, a set of two or more vectors are linearly independent when this vector equation here, where we have a constant times each vector equals a zero vector, only has a solution where all the c values are equal to 0. And because we have three vectors, we'll have c sub 1, c sub 2, and c sub 3. So we'll set up this vector equation, solve it to determine if they are linearly independent or linearly dependent. So our vector equation is going to be c sub 1 times vector v sub 1 plus c sub 2 times vector v sub 2 plus c sub 3 times vector v sub 3 equals the zero vector. So we'd have c sub 1 times v sub 1 plus c sub 2 times v sub 2 plus c sub 3 times v sub 3 equals a zero vector. Let's write this as an augmented matrix and then write it in reduced row echelon form. So we'll have a 3 by 4 augmented matrix where the first row would be 5, 14, negative 3, 0. The second row would be 2, negative 13, 5, 0. And the third row would also be 2, negative 13, 5, 0. So notice right away, row 2 and row 3 are the same. So let's obtain a row of zeros by replacing row 3 with negative 1 times row 3 plus row 2. Let's also get a leading entry of 1 in the first row. Notice that negative 2 times 2 plus 5 would be 1. Let's replace row 1 with negative 2 times row 2 plus row 1. So in the first row, we'd have negative 2 times 2 plus 5, that's 1. And then we'd have negative 2 times negative 13, that's 26, plus 14, that's 40. Negative 2 times 5, that's negative 10, plus negative 3, that's negative 13, and then we'd have 0. Second row stays the same. So because we have a row of zeros, we already know we're going to have an infinite number of solutions, and therefore the vectors are linearly dependent. But we still need to express a relationship between c sub 1, c sub 2, and c sub 3 in order to write vector v sub 3 as a linear combination of v sub 1 and v sub 2. So for the next step, let's get a 0 here by replacing row 2 with negative 2 times row 1 plus row 2. And we'll keep row 1 and row 2 the same for right now. So the first row stays the same. The last row stays the same. And now for row 2, we have negative 2 times 1 plus 2, that's 0. Negative 2 times 40 is negative 80, plus negative 13, that's negative 93. Negative 2 times 13 is 26, plus 5 is 31, and we have 0. Now let's get a leading entry here of 1 by replacing row 2 with negative 1 over 93 times row 2. So row 1 and row 3 stay the same. And then for row 2, we'd have 0, 1, and then negative 1 over 93 times 31 actually simplifies to negative 1/3. And then we have 0. Again, we multiply negative 1 over 93 times 31, we get 31 over negative 93. But 93 is equal to 3 times 31. The 31 simplify out, giving us negative 1/3. Let's continue on the next slide. For our last step, let's get a 0 here by replacing row 1 with negative 40 times row 2 plus row 1. So the second and third rows stay the same. And now for row 1, we'll have negative 40 times 0 plus 1, that's 1. Negative 40 times 1 plus 40, that's 0. Negative 40 times negative 1/3, that's 40/3. And then plus negative 13, or minus 13 over 1, common denominator of 3. So our denominator is 3. The numerator is 40 minus 39, which is 1. So we have 1/3 and then 0. So now the augmented matrix is in reducible echelon form. We already know there's a non-zero solution. Notice the first row tells us that C sub 1 plus 0 C sub 2 plus 1/3 C sub 3 equals 0. And the second row tells us that 1 C sub 2 or C sub 2 minus 1/3 C sub 3 equals 0. So here we know that C sub 1 must equal negative 1/3 C sub 3. And we know that C sub 2 must equal positive 1/3 C sub 3. So we can use these relationships to express vector v sub 3 as a linear combination of vector v sub 1 and v sub 2. Remember, our vector equation was C sub 1 times vector v sub 1 plus C sub 2 times vector v sub 2 plus C sub 3 times vector v sub 3 equals the 0 vector. So if we solve this for C sub 3 times vector v sub 3, we'd have C sub 3 times vector v sub 3 equals, we can leave off the 0 vector, and this would be equal to negative C sub 1 times vector v sub 1 minus C sub 2 times vector v sub 2. So if we want to write v sub 3 as a linear combination of v sub 1 and v sub 2, notice how C sub 3 would have to be equal to 1. And if we know C sub 3 equals 1, we have the equations here we need to find C sub 1 and C sub 2. So going back to our first slide, we now know the three vectors are linearly dependent because the solution to our vector equation was not just C sub 1, C sub 2, and C sub 3 equals 0. And again, now to express vector v sub 3 as a linear combination of v sub 1 and v sub 2, if we want v sub 3 here, notice that C sub 3 is equal to 1. So if C sub 3 is equal to 1, notice how this tells us that C sub 1 is equal to negative 1/3, and C sub 2 is equal to positive 1/3. But we need to be careful here because notice how the right side of this equation is negative C sub 1 times vector v sub 1 minus C sub 2 times vector v sub 2. So because C sub 1 is negative 1/3, the scalar here is going to be positive 1/3. So v sub 3 equals 1/3 times v sub 1. And then because we have minus C sub 2 times vector v sub 2, and C sub 2 is positive 1/3, this should be minus 1/3. Because we have a plus sign here, the scalar here is going to be negative 1/3. I hope you found this helpful.